All right. Hello there, Epidemics. If you don't have the chat window open, there's some cute puppy pictures in there. You might want to go check that out. All right. So this is the last lecture before spring break. So I will be getting assignments up tomorrow, more likely on Saturday, let's be honest. And those are not going to be due till after spring break. So you have until March 24th to complete these assignments. So next week, if you don't want to work on anything, you don't have to, not for this class. If you want to do the work next week, go ahead, give you some breathing room the following week. All right, so we're going to start by wrapping up our story of the 1918 flu pandemic. And then we're going to go on and we're going to talk about how new diseases come into the human population and what we can do to try and detect new diseases so that we can prevent the next pandemic. All right. So the 1918 flu, while it lasted for a little bit longer in Europe, by the end of 1918, it was largely gone from the US. Why did it stop? What happened here? Quite possibly herd immunity played a major role. Once enough people had gotten the flu, there weren't enough new people to infect, and we had herd immunity. The second option, also a possibility, is what we call attenuation. So that is attenuation, or we say the virus was attenuated. So if the virus attenuated, that means that it mutated to become a weaker strain. Attenuation is specifically for less infectious. It's not just a mutation, it's a mutation that causes the virus to be less contagious or less harmful or both. And it happens in a lot of diseases. We see this frequently, but remember, mutations do not guarantee attenuation. Sometimes the mutations go the opposite direction and things get more dangerous, more deadly. So we don't think of the flu nowadays as that deadly. It does kill tens of thousands of Americans every winter. So it is still a deadly disease, but not on the scale of the 1918 flu. This is one of the biggies in pandemic history. So how did this strain kill? Part of it was pneumonia. Pneumonia is, I'm going to give you the definition, inflammation of the lung with consolidation. So inflammation is swelling of the tissues. And we can get inflammation anytime we get an infection. You've probably noticed it if you've ever gotten a cut and it gets red and swollen. That swelling is inflammation. Consolidation means that the lungs were filling up. They were filling up with cell debris, dead cells. They were filling up with fluids that were leaking from the blood vessels. Because remember, we've got an infection, our blood vessels become a little bit leaky. And immune system cells. So the immune system reacted so strongly that there were too many immune system cells in the lungs. So areas of the lungs became solid or filled with fluid or clogged. And the lungs were no longer able to adequately get oxygen out of the air and get carbon dioxide from the bloodstream exhaled. So the gas exchange process failed there. Now, flu can also, like many viruses, interact with the immune response and inhibit that immune response. And when you have the immune response either inhibited or so busy dealing with the primary virus, which was probably the case with the 1918 flu, then there's an opportunity for what we call a secondary infection. So the immune system is busy over here paying attention to the 1918 flu, and here comes a bacteria that can cause bacterial pneumonia. And because the immune system is wearing itself out against the virus, it doesn't have the cells available, it doesn't have the resources to go after the bacteria. This is another very common thing in severe viral infections. The virus itself can cause damage, but it also gives an opportunity for a bacteria to get its foot in the door. And remember, back in 1918, we didn't have antibiotics. And the third thing that we talk about is a cytokine storm. So I've mentioned this term before, but I don't think I've defined it for you. White blood cells, cells of the immune system, release chemicals called cytokines. These cytokines are inflammatory, so they cause leaky blood vessels, they cause swelling, they activate or turn up the immune system, so they're ramping up the immune response. The idea between releasing cytokines is that that's going to bring a stronger immune response to the site of the infection. Sounds good, but the problem is if it gets to be too many cytokines, then we have hyperinflammation. And that can contribute to pneumonia. Cytokine storms are more common in young adults. And remember, the 1918 flu primarily hit young adults. So this is a likely problem with the 1918 flu, one of the reasons it was deadly among the young adults. So we've got these different things going on, including one of my cats having a grand old time in the other room, apparently. And all of these can contribute to death. It's not likely that everybody died from a cytokine storm or everybody died from pneumonia. It's probably some people died from one thing, some people died from a different thing. In response to the pandemic, many communities enacted anti-spitting laws. So before the 1918 flu, you know, people would spit on the sidewalk. It just happened. And then they passed laws against that. So we don't see as much public spitting as we used to. Some of these laws are still on the books. They're not really being enforced. Several states developed departments of public health. Public health is not the same as individual health. Departments of public health are not looking out for the individual, they're looking out for the community. So the idea here is that they can come up with strategies and enact measures to reduce the spread of diseases. So things like masking with early COVID and the shutting down of schools and businesses in the early wave of COVID, that was under public health. It wasn't to save one person's life, which is what your doctor tries to do. It was to prevent the disease from spreading through the community. Of course, in America, we are very much about the individual, so we really hate these kinds of measures. But remember, when COVID started, we had no idea how severe it was going to be. And it's pretty severe. It's not as bad as the 1918 flu. It's not as bad as the Black Death plague, but we're trying to prevent those kinds of things from happening by instituting these public health regulations. And the federal government formed, the National Institutes of Health, which was is a federal level public health organization. Again, trying to look out for the health of the entire population, not just individuals. If there was a 1918 style flu pandemic happening today, if this flu came back and it was as fatal as it was back in 1918, we could expect 2 million American deaths, or 240 million worldwide. COVID has killed almost 2 million Americans. Somewhere, last I looked, it was like 1.7 million American deaths, or 1.6 million American deaths. COVID has lasted longer than the 1918 flu, though. The 1918 flu in the US lasted about a year. So those 2 million deaths would have been in 1 year. Could be worse. It can always be worse. There's a strain of flu that's called H5N1. So hemagglutinin type 5 and neuraminidase type 1, those are your antigens on the surface of the cell. And these are usually avian flus. There is H5N1 going around in wild birds right now. And in fact, last year, it's been going around in birds for over a year now. And it's why the price of eggs went up so dramatically, because we had to, it got into poultry, it got into chickens. And when it gets into your flock of chickens, you got to get rid of them, unfortunately. Eric, go ahead.
I'm not sure how true this is because I just saw it like on a random website, but isn't there like a high potential that an avian flu could like wipe out most of the population? If it was like if it did cross over.
Yes.
Mm-hmm.
That's exactly where I'm going with this. When we see H5N1 avian flu spilling over into humans, the mortality rate is around 50%, which is very scary. The good news is H5N1 spills over periodically into people, but it usually doesn't spread very well between individual humans. So usually you'll get an outbreak, you'll get a few individuals or maybe a couple of hundred individuals who get infected. And it doesn't like spread throughout the entire community, out there through the entire world, which is a really good thing. The current H5N1 avian flu pandemic has been found in, has passed into people a couple of times. It is showing a roughly 50% mortality rate, but it's passed into less than 10 people. And there's no signs of it passing from one person to another. All of these people, and it's less than 10, have had direct contact with infected birds. Unfortunately, we're starting to see it showing up in other mammals, which is a bad sign. So it is showing up in sea lions, mink. It showed up on a mink farm, and wild foxes. When we're talking about a disease moving from animals to humans, the vast majority of them are coming from other mammals. Birds are like the second largest category source of diseases that jump into humans. So the fact that it's already jumping into mammals, yeah, that's concerning. It is something we should be watching. Now, today we have a vaccine for avian flu for domestic birds. So why aren't we vaccinating poultry? Why aren't we going through these chicken farms and vaccinating all the birds? Because a chicken farm can have tens of thousands of birds. And they usually don't keep the birds for very long time periods. Even the egg layers, birds are most prolific, chickens are most prolific egg laying in the first 1 to 2 years of life. So a lot of egg producers will cull, it's a very polite word for it, birds once they get over 2 years old. And meat chickens generally are slaughtered less than 1 year old. So it would be very expensive to vaccinate all of these birds for this. Hopefully, the fact that we have a vaccine for birds means that we can quickly develop a vaccine for humans if it looks like H5N1 is going to start spreading. And that's the other thing about the 1918 flu. We have vaccines for flu. We have the resources set up to make new flu vaccines every year to begin with. So if a new deadlier strain comes along, it's just a matter of the time needed to manufacture that vaccine. Virologists every year try to predict which strains of flu are most likely to become common in the following winter. It takes a while to build up a supply of the flu vaccine. It's not a fast process, unfortunately, but you know, they try and predict it the summer before the next flu season. Sometimes they get it right, sometimes they don't, but the flu vaccine that we get is protective against multiple strains. So it's not just one strain. The modern flu vaccine can use killed virus, it can use attenuated virus, or it can use just viral proteins. So we have options there. And if we're just doing viral proteins, then that makes it easier. We don't have to grow up large supplies of the virus. There is no way to get flu from the vaccine. A lot of people will go, oh, I got my flu shot and I was achy and I got a headache and I didn't feel good. Well, you can get those side effects from the vaccine, not so much the flu. And you get those side effects because your immune system is responding to the vaccine. So aches, maybe a fever, fatigue, they don't last as long as the flu, they're not as severe as the flu, and they are not life-threatening. So yeah, when I get my flu shot, I try and get it like on a Friday afternoon, so I can spend the weekend feeling like crap. But it's not giving me the flu. Okay, so that wraps up the 1918 flu pandemic discussion. Any thoughts, questions, comments?
Without the vaccine, how lethal would you say the current flu is?
It's highly variable from year to year. I think without the vaccine, we would probably see more like 100 to 200,000 deaths in an average winter. But that's an educated guess, and it's not a very educated guess.
Okay, fair.
Okay. So the next little bit I want to talk about is origins of new diseases and how understanding how new diseases get into humans could help us predict or possibly prevent the next pandemic. We're going to have more pandemics in the future. It's going to happen, but we can certainly reduce the risk. So we're going to spend some time talking about major diseases. So this is from a study, a couple of studies that looked at the major diseases in human history, the big ones that have killed lots of people. So we're talking about things like measles, we're talking about plague, we're talking about the 1918 flu. We're not talking about more obscure diseases like heartland virus, which you may never have heard of, or valley fever, may never have heard of that one either. So we're just looking at the big ones. When we look at the big ones, we find that there are different characteristics for pathogens that arise in tropical areas compared to temperate areas. So diseases that arise primarily from the sub-Saharan Africa region versus those that arise from Europe, North America, and places that are not tropical, like most of China. So we're going to talk about tropical diseases and temperate diseases. We're also going to note that most diseases that have human impact are from what is called the Old World. I don't like this terminology, but it's very commonly used. So we're going to use it. It's the easy way to make this statement. And the Old World is Africa, Europe, and Asia. And the New World is North, Central, and South America. We find that most of the diseases that impact humans are from the Old World. And most, possibly all, infectious diseases arise in animals and then move into humans. I'm sure there are some that are in humans that evolve. I mean, that happens. They do evolve in humans. But a lot of the new ones are coming from animals. And remember, when they can infect both humans and animals, we call that zoonotic. So this map is looking at confirmed outbreaks of new diseases. Over, let's see, what was the time period for this one? 96 to 2009. So when I say new diseases, we also mean things like Ebola that breaks out periodically. So these are new outbreaks for a 13-year time period. You can see there's a lot of them. And we tend to see most of them in places like Africa. We see them in Southeast Asia. We see more in South America than we do in North America. We're going to talk about why that is. But first, we're going to talk about the stages that infections move through when they're going from being a disease in animals into a disease that infects humans. So, stage 1 diseases are diseases that only infect animals. If these pathogens are found in humans, it's caused by direct contact with an infected animal. And most diseases that are in this category cannot infect humans very easily. So the H5N1 avian flu right now, we've had a few cases, but it's not happening every time a person interacts with an infected bird. The big example here is rabies. Rabies circulates in wild animals, and it only gets into people when a person is bitten. So that's a major way that rabies gets into people. There are occasional transplants from animals into humans. So when I say transplants, it's predominantly heart valves. So pig heart valves are the right size to go in the human heart. So if somebody has a problem with their heart valves, they can get one from a pig. We also see usually short-term organ transplants, again, often from pigs, just because of size issues. And these are usually short-term while somebody's waiting for a human organ to be transplanted. So these are not spread between humans. If you run into a person who has rabies, the only way you're getting it is if they bite you. And if you get bitten by a person or an animal, you should go talk to public health or go to the ER or go to your doctor, get the rabies vaccine, because rabies is 100% fatal. Little asterisk, there have been a handful of people who've survived, but it's a handful. So
is that like also transmissible through like human saliva, blood, etc.? Like if you're not bitten?
it would have to be blood transfusion. It would not be through kissing or anything like that.
So it would need to be like blood to blood. It would have to go into your bloodstream.
It has to go into your bloodstream, yes.
Okay.
I wouldn't recommend it, but you could drink a vial of rabies vaccine or not vaccine, rabies virus, and as long as you didn't have open sores in your mouth, you'd be fine. Okay, stage 2. Generally speaking, for stage 2, again, we've got pathogens that circulate through animal populations. Again, oh, I'm sorry. Rabies is the stage 2 one. Sorry about that. Stage 1 agents are only found in animals, except for organ transplants, which is pretty darn rare. Stage 1s are often limited to a single host species or a group of closely related species. So a disease that would infect, say, dogs, wolves, and foxes So only those related species. Rabies is a stage 2 disease. Stage 3 are diseases that have limited human to human spread, and these cause a limited outbreak. So these are, again, diseases that primarily infect animals. They get into the human population and generally disappear relatively quickly. They do not become widespread, but they can infect a community, for example. And there are a good number of diseases that are stage 3 diseases. Ebola is our prime example here. Ebola outbreaks happen periodically. They can last months, up to the longest one that I found notes on was 2 years. So a few months to a couple of years. They're always localized to a small area, often just in one or a couple of countries, only found in Africa. The cases that have been found in other countries are all from people who were in Africa when the outbreak happened. And they just caught it in Africa and took it home. Stage 4, again, we're getting outbreaks from animals. Again, it's a disease that naturally occurs in animals, but it also infects humans. And this happens at a more commonly than a stage 3 outbreak. So it'll be things like dengue, yellow fever, cholera. You get these outbreaks that happen from time to time, and when they get into people, they can spread between people. Right now, there is a cholera epidemic. It's a worldwide cholera epidemic. We don't hear about it because it's primarily spread between people in less sanitary conditions. So this is not something that is likely to get into people in developed countries with relatively high sanitation, and I mean bathroom sanitation, but having bathrooms and not drinking out of a stream kind of sanitation. So they're not consistently found in humans, but they do have periodic outbreaks.
That made me think. I went to Italy over the summer, and as you guys probably remember, like Italy had a high outbreak of COVID when it started.
Yes.
They have public fountains all over the place, and it's like one pipe stream that just travels down, and people are like sticking their water bottles in there, scooping with their hands and stuff. And I thought that's probably why this country got so infected so easily.
Yeah, that could definitely have something to do with it. And that could spread cholera. Yeah. That infrastructure is probably hundreds of years old, though. That method of getting public drinking availability. Okay. Stage 5 are diseases that only infect people. They're no longer spreading in animals. And so these pathogens, these stage 5 pathogens, can become stage 5 pathogens in one of 2 ways. One, it's an ancestral pathogen that has existed in our species since before the human lineage separated from chimpanzees around 5 million years ago. So it's something that's been in people for a very, very long time. The other is an animal pathogen that has colonized humans more recently and has evolved to become specialized in humans. So HIV is our example of this. it moved into people in the early 1900s, and nowadays it only spreads between people. It's not always easy to figure out if a new disease, a disease that's causing illness that hasn't been seen in people before, has evolved from a pre-existing human pathogen or a human infecting infectious bacteria or virus. We wouldn't call it a pathogen if it didn't cause disease, or if it moved into us from animals. So we have lots and lots of bacteria and viruses that live on and inside of our bodies constantly. And most of the time they're harmless, but there's always the possibility that they can mutate and become pathogenic. For most of the major diseases that have been studied, it appears that they have originated from a more recent move into humans. So not 5 million years ago, although there are a couple of those, but from, say, the past 11,000 years. And I say 11,000 years because 11,000 years ago was when we started having agriculture. When we started having agriculture, we started domesticating animals. We started living with pets. We started living in closer quarters with other people. We started staying in the same places year round rather than traveling frequently. So that really helped a lot of diseases get established in the human population. I mean, you can picture this. A disease moves into a hunter-gatherer community. Everybody in the tribe gets sick. Half the tribe dies. The survivors either start rebuilding the tribe or move into neighboring tribes. But they do that after they've recovered from the disease. So you're not getting a lot of transmission. If everybody lives in cities and we start having long distance trade routes, then it's much easier for diseases to establish in a population and spread from community to community. Okay, so these are the stages that a disease has to go through. They can go from one stage to the next. So a disease can be only in animals. It can spread rarely into people and not spread from person to person. Then it can mutate and spread occasionally from person to person. Then it can mutate and spread readily between people. And then it can mutate further and only be a human-specific disease. All right, so that's the process in very simple terms, obviously. Now we're going to talk about characteristics of diseases that help influence whether they get into people and how they're going to act in people. So we're going to talk about tropical versus temperate diseases. So these areas in red, these are the tropical parts of the world, roughly. It has a lot to do with climate, moisture, not having a winter. That's going to be very important here. Diseases that have originated in these tropical climates are different than those that originated in temperate climates. When we talk about those that emerged in temperate climates, I'm sorry, again, we're going to be focusing on Europe and the Middle East, because that's where I can find information from. I don't have good information out of Asia. So, tropical diseases are more likely to be transmitted by insect vector. We talked about this term way at the beginning of the semester. So that means a biting insect. So a mosquito or a flea, kissing bugs. There's a bunch of different insects, flies that can transmit diseases. We don't see very many temperate diseases spread by insect vectors because of winter. And winter causes insects to either die off, so the population reduces, or they kind of go into some type of hibernation, so they go dormant, and so they're not spreading diseases during the winter. A lot of diseases that are transmitted by insects actually cause harm to the insects too. So insects that are infected, say there's a mosquito that's infected with malaria and it's in the Boston area, it's not likely to survive the winter because it's going to be sick from malaria. Another thing we see with tropical diseases is that they produce a weaker immunity and a shorter immune memory. We don't know why this is, but it is seen over and over and over. So diseases that are in tropical areas can come back and reinfect individuals over and over and over again. People will be immune for a while, but then they can catch it again. Tropical diseases tend to last a relatively long time period. So temperate diseases tend to be short term. The patient either dies or recovers. They last maybe up to 2 weeks. Tropical diseases can last for months, years, or even decades. Usually if they last decades, they don't cause a severe infection. They can even, they can go into a dormant state, for example. And in that dormant state, they can not cause much in the way of illness. And then they can reemerge later. So they can have latent periods. We think that some of the characteristics of these tropical diseases are related to population density. Because in historic times, population density was definitely higher in temperate climates, in Europe, in the Middle East, in lots of places in Asia. So if you've got an area like Africa, where the population density is relatively low, for a disease to be able to survive by infecting people, it needs to be able to reinfect. It needs to be able to last a long time, so the person is contagious for a long time. And insect vectors can transmit diseases from one community to another, which is not something that's needed in these more densely crowded places that we saw in Europe in the relatively long historical past. Okay, yeah.
Would it lasting longer in the body like possibly have something to do with like the fact that the virus is like heat resistant kind of, so if our body has a fever, the response would be different?
That's an interesting hypothesis. I don't think that's relevant. It might, most viruses do not survive long-term outside of the body.
Mm-hmm.
So I can see that with maybe bacteria.
Okay.
But viruses, they pretty much have to get into another potential host, usually within a couple of hours.
Uh-huh.
And then if they don't, then they're
They
not
just die
infectious.
off. Yeah.
Yeah. Okay. Temperate diseases. The majority of diseases that arose in these temperate areas are crowd epidemic diseases. This means that they need a relatively large population with a lot of mixing. They have to have fast and efficient transmission between individuals. It requires immunologically naive populations. So that's the mixing as well as the large population. You're more likely to have immunologically naive people when you have lots and lots of people, lots of babies being born. Babies are always immunologically naive, as well as trade routes. When we look at some of the specifics, measles and whooping cough require a population size of several 100,000. So we're talking, decent size city. And this population can be in one community, or it can be in a cluster of smaller communities that has frequent trade. So you can imagine if you live in Danvers and these were more isolated communities, you might trade with the city of Lynn. Lynn is on the coast, Danvers isn't. Maybe you trade with Lynn or Salem or Beverly for seafood, but you can grow crops. And so you grow apples and you trade your apples for the seafood. And so you have regular trade routes in between the communities. Each community might not have 100,000, but when you add them together, then they do. So this also is related to agriculture and domestication. There was a steep, a very steep rise in human population around 11,000 years ago when we started doing agriculture and domesticating animals. So agriculture, new diseases, new characteristics that allowed diseases to spread. So tropical diseases infect small populations, usually can be found in humans and animals, do not produce long-lasting immunity. Temperate diseases, more acute infection, spread rapidly between individuals, need a higher concentration. So, graphic image ahead. This is guinea worm. This is the parasite. It causes extreme pain. It can cause inflammation. It can cause fever. It causes major, major fatigue in individuals. The sensation of the parasite is linked, it is said to make you feel like your foot is on fire. And the guinea worm, regardless, the guinea worm infects people from drinking supplies. So you drink the egg of this parasite, it hatches, it grows, and then it migrates down your leg. And it starts creating that hot burning sensation. What do you do if you feel like your foot's hot and burning? You put it in water. And when you put it in water, the parasite comes to the surface, you get this little wound, and it starts laying eggs. And so the eggs are released when the foot is in the water. And that's why this person's foot was wet. It was to bring the parasite to the surface of this open wound. Guinea worm can be extracted, but it's not easy. They've got, it looks like a piece of gauze. Traditionally, you would use a stick. You would bring the worm to the surface and start winding it around a stick. Gradually, very gently, pulling it out of the wound. This might take multiple days of, wind it up for a little bit and then let the worm chill out. It's a parasite, it doesn't really think, but it will, if it feels like it's being pulled out, it will try and hold on inside the person's foot. So you may have to let it relax and then pull some more. The guinea worm is almost eradicated. This was a big, big move by Jimmy Carter. He almost got there. Well, okay, he's in hospice now, 98, I think it is. I think there were 12 cases, confirmed cases of guinea worm in humans last year. Anyway, it was a very small number. So hopefully in the next couple of years, this one will be eliminated completely. Okay. So where do pathogens come from? 75% of newly emerging infectious diseases come from animals. And diseases that are not new, 60% of infectious diseases are those stage 4 infectious diseases that can circulate in people and circulate in animals. So stage 3 and stage 4. Zoonotic diseases are responsible for around 2.5 billion illnesses worldwide and 2.7 million deaths every year. So the majority of the diseases that we deal with are zoonotic, and newly emerging diseases are the ones that are more likely to be deadly. So we're going to focus in on zoonotics for a bit. And what we see are 3 major origins: rats and bats, domestic animals, and primates, especially apes. I guess we could also say wild animals that are consumed for food. So when we talk about the temperate diseases, the ones that we know where they came from, they generally come from rats, bats, and domestic animals. So these are the temperate diseases. Rodents and bats are very comfortable around people. It's not uncommon to find bats roosting in houses or under the eaves. Whether we like it or not, pretty much everybody has mice in the walls of their houses or apartment buildings. So these are very, very comfortable around us. Rodents in particular like domestic food caches. So if you've stored food, that's going to attract rodents. If you have food waste in the trash, in the compost, in the dump, rodents are going to find that. Every time I've had a problem with mice in the house, they've almost always gotten into cereal boxes. It's food for them. I only had that in one place I lived. That was, yeah, not fun. Domestic animals tend to live in more crowded conditions than wild animals. They tend to live closer to people. Of course, they're domestic. And we have regular interactions with them. We have farm workers dealing with cattle and pigs and chickens. We have domestic pets that live in the house with us, dogs and cats. Back in the Middle Ages, and before that, even nowadays, sometimes it's not unusual to have livestock in the house, often on a temporary basis. So a lot of the times this is young animals, newborn goats or sheep, cattle that are needing a little bit of extra TLC, or the weather's gotten extreme and they're not old enough to deal with the really cold weather. They'll be brought in the house sometimes. And back when everybody lived in like one-room houses, you bring in a cow or two. You may have one or two cows. You bring them in the house, and guess what? That's a source of heat for the house for the winter. So it helps warm up the house for the people. And this is, as I mentioned, largely temperate diseases. Domestication started in temperate climates. And it's constantly, consistently been more common in temperate climates. It's becoming relatively common on the continent of Africa for the past couple of hundred years, and other tropical areas like that in the past couple of hundred years. When we talk about tropical diseases, we're talking about coming from primates, especially the apes. We are primates. Apes is a subcategory of primates. So apes are gorillas, chimpanzees, and humans. So we are more closely related to these organisms than we are to pigs or dogs or cats, which means there's less of a species barrier between us and pathogens. So it's easier for a disease that infects primates, especially apes, to jump into us because we've got a more similar immune system. We're more likely to have the right proteins on the surface of our cell for them to infect. It's believed that primates have contributed to 20% of the major human diseases. 20% came from primates. Primates are only 0.5% of vertebrate species. So on a global scale, they're not that common, but they contributed the most. And then when we talk about wild animals, so primates are going to be primarily tropical diseases because primates occur in tropical areas. Wild animals, that can be either temperate style or tropical style diseases. And these guys, didn't mean to use that big of a pen. These can be either. And I typed in here originally consumed for food. So we're talking about hunting. We're talking about raising non-domestic species for food. So if you've ever been to a restaurant and ordered venison or rabbit, well, rabbits are domesticated now. If you've ever ordered venison off the menu, it came from a farm. We farm deer for venison. In other parts of the world, there are lots of other exotic animals that are farmed for venison. Americans are not as adventurous with the types of things that we eat for food as some parts of the world. We also have to think about dogs and cats. These are the animals that, why am I putting this under wildlife? Good question. Dogs and cats, they come in the house, might sleep in the bed with you. They cuddle. Well, if they go outside unsupervised, chances are they will interact with wildlife. And when I say interact with wildlife, I mean fighting or hunting. So your beloved cat goes hunting, and if your cat goes outside unsupervised, it probably hunts something, mice, birds, something. And then if it catches a disease from that wildlife, it comes and it's sleeping on the pillow next to your head all night, breathing in your face, and we have a zoonotic disease. Okay. So I mentioned that the vast majority of major human diseases arose in the old world. And I mentioned that the old world is this part of the globe here, Africa, Europe, Asia. Why? Anybody have any ideas why diseases would be more, why more of our diseases would come from the old world than the new world? No ideas? Okay, that's fair.
More wild animals?
Well,
Is there
no.
like more species or something?
That's a good guess. Certainly there is a more diversity of species, because frankly, the old world is a lot bigger than the new world. Any other ideas?
Maybe because there's a lot of like isolated communities that don't often interact still, and we wouldn't know about an outbreak because the countries are less developed.
Mm,
Until it was spread, no one would know about it.
okay, that's an interesting thought. That actually applies more to a lot of places in South America than Europe.
Right.
So we know that the deadly diseases from Europe were brought over to the Americas and helped the Europeans invade and conquer the Americas. And these diseases were much more devastating than anything else the Europeans did when they came over. We've talked about this before, wiped out huge percent of the native population in the Americas. There were no comparably devastating diseases that went and attacked the Europeans. So the first thing I'm going to talk about, domestication. In the old world, we have goats, we have cattle, we have sheep, we have pigs, we have chickens, we have cats. All of these animals were domesticated from wildlife in the old world. So there was a lot of domestication in the old world. In the new world, the natives had dogs, so they brought dogs with them when they crossed the barrier to get to the new world. But Other than that, it's largely like llamas until relatively recent. And they didn't use llamas for milk. They did not keep llamas indoors, so they weren't living in quite as close contact with them. They were pretty much used for carrying loads, and probably for meat, maybe for their wool. So that's number one. It's just the difference in the number and diversity of domestic animals. This is pre-European colonialism of the New World. The other is the primates. So there are primates in Central and South America, just like there are in Africa, in Asia, in parts of Europe. But the primates that live in the New World are evolutionarily more distant from us than the primates in Africa. We evolved in Africa 5 million years ago. By that point, the New World primates and the Old World primates had already separated, evolutionarily speaking. So we are more related to Old World primates than to New World primates. And time. We've been in the Old World for 5 million years. I mean, that's the entire history of our species. The Native Americans moved to the New World around 18,000 to 26,000 years ago. This means there's been a lot longer time for pathogens to jump into humans in the Old World and evolve to become infectious to us in the Old World than in the New World. Certainly when humans crossed from Russia to Alaska, they brought some diseases with them, but the diseases that already existed in the New World had not seen people before, so they weren't as able to infect humans as the diseases that had, kind of evolved alongside us over the years. So those are the three big reasons why we think the Old World is the source of the majority of serious diseases that humans have to deal with. How does this information help us? Well, we don't always know the origin of many pathogens. There are some that we have never found in the wild. We have not found COVID in the wild. We found very closely related viruses in bats in Asia, but we haven't found COVID-19 itself. We have no idea where Ebola is when it's not infecting humans. We know it's not in the great apes like gorillas and chimps because it kills them at high numbers just like it kills people at high numbers. Not sure where it is, how it gets into humans, where these outbreaks start from, and we've been looking for 26 years. Some we haven't even found similar diseases in animals. So even though we don't know for sure where some of the diseases that impact us have come from, having an understanding of the origin of some of the major human pathogens allows us to potentially develop a monitoring protocol to help spot newly emerging diseases. Most of these new emerging diseases come from animals, so really monitoring should focus on people with regular exposure to animals, especially wild animals. So we're looking at people who are hunters. We're looking for wildlife rehabilitators, especially wildlife veterinarians, zoo workers, people who go caving a lot, other people who work with wildlife, like game wardens. Okay, I see something came up in the chat. Okay. These groups regularly get infected with new diseases. They don't usually get sick from them, but you can find them in their bloodstream, or you can find antibodies in their bloodstream. These are infections to watch. They've moved into a person. Even though they can't spread from person to person, we should be keeping an eye on them. And there are places where we're doing this. In Cameroon, there's a program that monitors people who hunt for new diseases. We've talked about monitoring the health of dogs and cats because they're more likely to interact with wildlife. They're more likely to have a disease that they can then pass on to us because they're in such close contact with us. So monitoring their health is important. Monitoring wildlife die-offs. I mentioned earlier about the H5N1 outbreaks in sea lions and foxes, wild animals that are getting this very deadly form of avian flu. And there's this program, this concept that's called One Health. It is initiated, it's an initiative designed to help improve human health. One focus of it is infectious diseases. So One Health looks to make humans healthier by monitoring health in animals and by monitoring and improving the health of ecosystems. A polluted ecosystem means more harm for human health. Poor animal health means more diseases in animal populations, which could potentially jump into humans. So we're adding food and water safety here. We add nutrition here. We add combating the rise in antibiotic-resistant bacteria, as well as identifying and dealing with emerging zoonotic diseases. It's a collaborative approach. There are major programs in the World Health Organization and in the CDC. The CDC monitors diseases that can potentially infect humans, primarily by looking at animals in the food supply or the exotic pet trade. So in the US, the majority of zoonotic outbreaks are Salmonella. Salmonella can be found in pet food. It's found in cattle, pet store puppies, reptile and amphibian pets, poultry, including flocks of backyard chickens, small mammals, wild songbirds. So watching for Salmonella outbreaks in those populations can help us restrict or fight off infections in humans. In an ideal world, this would be a very well-funded and widespread program. And I know we're almost out of time. Give me 1 minute. There are an estimated 1.7 million viruses in mammals and in birds that could potentially infect people. So there's a lot of diseases out there. And some people want to look for all of these diseases. That's not really practical, right? So there's a school of thought that says we should be looking at these viruses in animals, not just in people, where spillover is likely. So looking in species that are hunted commonly, looking at exotic pets, looking at non-domestic species that are bred for food. Okay. Woo. And that is that. Any questions? I know I was rushing a little bit at the end there.
All set.
All set? Okay. Remember, we got spring break next week. Woo! So, so I won't see you until the 21st when we start talking about the Black Death, the biggie. See you guys then.
Thank you. Have a good one.
Thank
Happy
you.
spring
Have a
break.
great break.
Thank you.
Bye.